Sorry, I started recording. What did? If you're talking to me. Okay, so so this theorem is just saying that if you have a vector space V, then a W is a vector subspace of V if and only if these two things happen. One, if you have two vectors in W, their sum is also in W. And if you have a scalar K and a vector U in W, then KU is also in W. The words for these two properties are closure in W under addition and closure in W under scalar multiplication. If you have closure in W under addition and scalar multiplication, then that's equivalent to saying that W is a subspace of V when W is a set of one or more vectors in a vector space V. Okay. Usually, almost always, W would have to be a lot more than one vector in order to be a subspace of its own, in order to be a vector space of its own, because it has to be closed under addition and scalar multiplication. Once you have a single vector, if you have a vector space that's large enough, once you have a single vector in it, you would then need every scalar multiple of it, and you would need every addition of it with another vector. So just having a few vectors, you already have a very large space. Okay. So I showed how the zero vector space is a subspace of any given vector space because every vector space contains 0. Okay, we talked about symmetric matrix and how symmetric matrices are vector subspace of M sub n, how upper triangular, lower triangular matrices, diagonal matrices are each subspaces of M sub n. M sub n is the vector space of n by n matrices with standard addition of matrix operation and standard scalar multiplication of a matrix operation. Okay, this definition is the definition of a linear combination of vectors. And so W is a linear combination of vectors V1 to VR if W can be expressed using this equation where the K's are scalars and the K's are called coefficients of the linear combination. I'm saving this recording. Okay, I have this recording. So if S here is a non-empty set of vectors in the vector space B, then the set W is of all possible linear combinations of the vectors in that set S is a subspace of B. Okay, and it's the smallest subspace of B that contains all those vectors in the set S. Okay, and so I talked about the span of a set of vectors, and I showed how given two vectors U and V in R3, we can show how a vector is a linear combination of those two vectors and how another one is not a linear combination of those two vectors. And so I did all this work here to show that. And the homework for this class is 4.1, numbers 7 and 9. Okay, so we now went over quickly last lesson. Anyone have questions about the homework due today? Homework 4.1, numbers 7 and 9. Any questions? Okay, so this lesson, we are now going to continue where we left off. So, first is a problem, example 15. Okay, so determine whether the vector V, which is equal, whether V1, which is equal to the vector 1, 1, 2, V2, which is equal to the vector 1, 0, 1, and the vector V3, which is the vector 2, 1, 3. Determine whether those three vectors span R3. Okay. So solution, right? So remember that the meaning of a set of vectors spanning a space is that any vector in the space can be represented as a linear combination of the vectors in the set of vectors. Okay, let me say it another way. So in this problem, to find that those three vectors span R3, we need to show that any vector in R3 can be expressed can be expressed as a linear combination of those three vectors. Okay, so in this problem, to find that those three vectors span R3, we need to show that any vector in R3 can be represented as a linear combination of those three vectors. The span of these three vectors is the set of all linear combinations of those three vectors. To show that the span of those three vectors is R3, or that they span R3, we need to show that the set of all linear combinations of those three vectors is equal to R3. Okay, we know that any linear combination of those three vectors is an element of R3. So the set of all linear combinations of those three vectors is a set entirely contained in R3. And so we want to show it not only is it in R3, but it's all of R3. Okay. Okay. So we must determine whether an arbitrary vector W, which is equal to W1, W2, W3. Again, we use B. Whether an arbitrary vector B, which is B1, B2, B3 in R3 can be expressed as a linear combination of V1, V2, V3. Okay. So as a linear combination, B is equal to K1, B1 plus K2, B2 plus K3, B3 of V1, V2, V3. Okay, so we want to show that this can happen, this equation. Okay, well, so saying that equation is saying that the order triple V1, V2, V3 is equal to K1 times V1, which is 1, 1, 2, plus K2 times V2, which is 1, 0, which is 1, 0, 1, plus K3, which is 2, 1, 3. Okay, and so then this is equal to, you have K1 plus K2 plus 2K3 as the first component on the right-hand side. The second component is K1 plus 0K2, which is 0, plus 1K3, which is K3. And the third component is 2K1 plus K2 plus 3K3. And so you're just finding each component one at a time, right? So 1 times K1 plus 1 times K2 plus 2 times K3 would be the first component, and then you find the second and third. So you have the components on the left-hand side are equal to the corresponding components on the right-hand side. And so from this one vector equation, you have 3 corresponding equations, one for each component, setting the components on either side to be equal to each other. So you have K1 plus K2 plus 2K3 is equal to the first component on the left-hand side, B1. You have the second component, K1 plus K3 is equal to B2. Okay, and you have the third component, which is 2K1 plus K2 plus 3K3 2K1 plus K2 plus 2K3 is equal to B3. Okay, and so you now have those 3 corresponding equations. So the question, the corresponding question for this problem here is this system consistent, have at least 1 solution for any for all values of B1, B2, and B3. So for all possible values of B1, B2, and B3, for all ordered triples B1, B2, B3, are there values of K1, K2, and K3 that would solve all three of these equations? Meaning, are there values of K1, K2, and K3 such that this equation holds for any choice of B1, B2, B3 on the left-hand side? Okay, so we want to show that there's at least one, we want to find out whether or not there's at least one solution for all the Ks for any choice of B1, B2, B3 in these three equations. Okay, so by an earlier theorem, which was by theorem 2.3.8, and so this is part C of that theorem and part G of that theorem. This is, or the equivalence theorem, but this is called the equivalence theorem. It's the one where you have all those statements that are equivalent. We have that the determinant of your coefficient matrix is non-zero if and only if AX equals B is consistent for every B. Okay. So you can know whether or not your matrix equation AX equals B is consistent for every B, depending on it's E and G. Okay, thank you. Yeah, okay. It's E and G. Okay. E and G. Okay, so by theorem 2.2.8 E and G, or the equivalence theorem, you have the determinant is non-zero if and only if AX equals B is consistent for every B. Okay, so because the determinant of A is equal to the determinant of is equal to the determinant of the coefficient matrix, determinant of the matrix 1, 1, 2, 1, 0, 1, 2, 1, 3. Okay, and so that's your coefficient matrix, which you get from here, because the A's are right with the coefficients there. K's, and so now you can find that determinant, and so you can take the cofactor expansion anywhere you want. Okay, so let's take it along the second row. So if you take it along the second row, the first thing is the 1, but it's a negative of that because it's you have a negative sign associated with that entry. And so it's -1 times the determinant of 1, 2, 1, 3, and then it's negative, and then the next thing is plus, and then you have minus again, -1 times the determinant of the corresponding submatrix, which is then 1, 1, 2, 1. Okay, and so then this is equal to -1 times 3 minus 2, which is the determinant, minus 1 times the determinant, the other one, which is 1 minus 2. And so this is equal to -1 times 1, which is -1, minus 1 times -1, which is -1. So this is equal to 1, -1 plus 1, which is 0. Okay, so you calculate that determinant, and you get the determinant equals 0. Okay, so this statement is saying that the determinant of A is non-zero if and only if AX equals B is consistent for every B. So since the determinant of A does equal 0, it is false that the determinant of A does not equal 0. Okay, so by the statement double star, by statement double star, the statement AX equals B is consistent for every B is also false, right? Because saying one statement, if and only if another statement is true, is saying that both statements have the same truth value. Not that either is true or false, just that they have the same truth value. And so saying that term A equals 0 means term that A is not 0 is false, which means that ax equals b is consistent for every b has the same truth value of false. And so by double star, we know that this statement is false. Okay, so since ax equals b is consistent for every b is false, we know that ax equals b is not consistent for some choice of b, little b. Therefore, there is some little b, which is equal to b1, b2, b3 in R3 that cannot be expressed as a linear combination of b1, b2, b3. Okay, and so since that's true, that means that b1, b2, b3 do not span. That means b1, b2, b3 does not span R3. Okay, there's some vector b in R3 that cannot be expressed as a linear combination of b1, b2, b3. And so the set of all linear combinations of b1, b2, b3 is not all of R3. Okay, so it doesn't span R3. So that's the end of that example. Next is theorem 4.2.4, which says that the solution set of a homogeneous linear system, ax equals 0, of m equations in n unknowns is a subspace of Rn. We call it the solution space of the system. Okay, it is a subspace of Rn. Okay, that's weird that you can, so you have a linear system and you can actually get a vector space from its solutions. So if you have a homogeneous linear system from this matrix equation ax equals 0, the word homogeneous is saying that the constants on the right hand side are all 0. This is, remember, this 0 is a vector. It's not, it's a matrix vector. It is not a, it's a matrix. It's not a number 0, excuse me. This is a matrix equation. A is a matrix, X is a matrix, and 0 is a matrix, representing a linear system, and it's homogeneous because this is a 0 matrix. So the solution set, the set of all X that satisfy this matrix equation, is a subspace of Rn. And we call it the solution space of the system, is a solution space of Rn. Okay, how you know, so the reason that that is the solution space of the system is a subspace of Rn is first, notice that solutions of the matrix equation, so that solutions X of the matrix equation, ax equals 0 are n by 1 matrices. Okay. Okay, are n by 1 matrices. So you can think of solutions X as vectors in Rn. Rn is the set of all n tuples. An n by 1 matrix is a matrix with n entries. It's just another way of representing a list of n things. Okay, so it's just another way to express the same, illustrate the same thing. And so solutions X of that matrix equation can be thought of as vectors in Rn. Since we know that Rn is a vector space, we can prove that the set of all solutions to this linear system, this homogeneous linear system, is a vector subspace of Rn by showing it is closed under addition and scalar multiplication. Okay, so if you have one solution, ax1 which equals 0. Excuse me. And you have another solution, ax2, and that equals 0. So ax1 equals 0 and ax2 equals 0. Then if you looked at a times x1 plus x2 in the parentheses, this would equal to ax1 by properties of matrices. This would be equal to ax1 plus ax2. And since ax1 is 0 and ax2 is 0, this is 0 plus 0, which is 0. So I just showed is that x1 plus x2 is also a solution of the matrix equation. This shows that that the solution space is closed under addition. Okay, and you also need to show it's closed under scalar multiplication. So given that ax1 is equal to 0, if you want to talk about a scalar multiple of x1, meaning kx1, well, a times kx1 is equal to k times ax1. And since ax1 is already known to be 0, it's k times 0, which is 0. And so what we showed is that kx1 is also a solution of this of the linear system, given that x1 is. And so this shows that the solution space is closed under scalar multiplication. So the solution space of a homogeneous linear system is a vector subspace of Rn. Okay, given that you have m equations and n unknowns. So solution is a homogeneous linear system with m equations and n unknowns, with m equations and n unknowns. Okay, you have n unknowns because you have vectors in Rn as solutions. Okay, so that's a proof of theorem 4.2.4. Okay, so next is example 16. Okay, so part A is let's say you have this matrix equation 1, -2, 3, 2, -4, 6, 3, -6, 9. And then it's times this matrix, which is x, y, z. And this is equal to the 0, the 3 by 1, 0 matrix. Okay, so we want to find the solutions of that linear system. Okay, so, well, let me tell you, the solutions are x is equal to 2s minus 3t. Y is equal to s, and z is equal to t. So we could do this from earlier. And so from that, it follows that x is equal to 2y minus 3z, or that x minus 2y plus 3z is equal to 0. Okay, so we now have the equation x minus 2y plus 3z is equal to 0. Okay, we have that equation now. So this is an equation of a plane through the origin that has this vector n, which is equal to 1, -2, 3 as normal. Okay, why? Well, because the point 0, because 0, 0, 0 is a solution of the equation. You can plug in x, y, and z to be 0, and the left and right hands of both sides are both 0. The equation holds. Because that is the solution of the equation, it means the solution space contains the origin. Okay. Also, the normal vector to an equation of a plane of the form, I already said this earlier, but I'll say it again. So a1x plus a2y plus A3 z is equal to 0. So the normal vector to an equation of a plane of that form is the vector n, which is equal to a1, comma a2, comma a3. Remember, you need that your equation to be of this form. It has to equal 0 in order to an equation of a plane through the origin. But okay, so well, yeah, let me. You could do it without through the origin, but what we're doing here through the origin. So I'll be specific so that you can learn from an example. So for this example, it's through the origin. Okay, so there's no plus constant here, so you don't have to worry about that here. So then n is the coefficients of x, y, and z respectively. The first component is the coefficient of x, the second component is the coefficient of y, and the third component is the coefficient of z. That's normal. Okay. And so our conclusion is that the solution set of the given linear system is a plane through the origin that has that normal vector n equals 1 comma negative 2 comma 3 as a normal. Okay, so there's a way to visualize geometrically solution spaces. You can think of them as planes. Other cases you can think of them as lines or other shapes. Okay, well, I guess in larger dimensional spaces, other planes. Okay, so that's explaining that. New idea. Okay, new thought. Okay, so let T sub A be from R n to R m. Okay, so let TA be from Rn to Rm be left multiplication by the coefficient matrix capital A. Okay, so T sub A is left multiplication by the coefficient matrix A. So what is that? So I'll remind you. So, well, okay, so we have T sub A, which is left multiplication by coefficient matrix A. So T sub A is a map from Rn to Rm. So if you have, that's an M. Okay, so if you have a vector of unknowns, an unknown vector x1, x2, dot, 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 x sub n, those are your unknowns in that matrix, you would left multiply it by coefficient matrix A, right? So you have A1, 1, and then A1m, A1n, and then it would be dot, dot, dot. This would be AM1, and then dot, 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 AMN. So there are m rows and n columns of this matrix. This is the coefficient matrix A. This is X. Okay, and so that this is the map T of X, T sub A of X. You're taking a vector X in Rn and left multiplying it by A. So this is T sub A of X. And the result is, well, if you take an m by n matrix and you multiply it by an n by 1 matrix, since the inner entries are the same, the outer entries determine the size of the resulting matrix, and so you get an m by 1 matrix here. And so you have corresponding values. So you have y1 to ym, and so this is an m by 1 matrix. So the T sub A as a function, T sub A as a function, left multiplication by matrix A, T sub A, the input is a vector X, which is in Rn. See how the X is in Rn, and the output is a vector Y in Rm. So this map T sub A has an input, an n tuple. Right? You're inputting an n tuple, and then the result of left multiplying by A, the result is an m by 1 vector or an m tuple Y in Rm. So this is a map from Rn to Rm, left multiplication by a coefficient matrix A. Okay. So let T sub A from Rn to Rm be left multiplication by the coefficient matrix A. The kernel of this matrix transformation is the set of vectors in Rn that T sub A maps to 0 in Rn. Okay, so the kernel of this matrix transformation is the set of all vectors in Rn that T sub A maps to 0 in Rm. Okay, so here in the whiteboard you have this T sub A, right? And T sub A as a map is from Rn to Rm. So if you visualize this as an arrow diagram, T sub A is a map that will map Rn to Rm. Now, some of the vectors in Rm will go to 0. So let's say some of these vectors will go to 0. So excuse me. So T sub A will map some of these vectors to single point 0. Okay. This set in the domain Rn, this set is the kernel of T sub A. The kernel of T sub A is the set of all things in the domain that get mapped to 0 by your function. So that's the kernel of T sub A. That's set in the domain. It's not the point in the codomain. It's just the point in the domain. The points in the region in the domain, right? And then everything outside of that still gets mapped by T sub A. It's just getting mapped to something other than 0, right? So all these points are still being mapped by something to something, but they're just points that are not 0. So that all those other points outside of that set are being mapped to something other than 0. And so the kernel of T sub A is a set of all things in the domain that T sub A maps to 0. Okay. So a matrix transformation is a function, and so the T sub A, and it's just the set of all things that T sub A maps to 0. Okay. Theorem 4.2.5. If capital A is an n by n matrix, then the kernel of the matrix transformation, T sub A, which is from Rn to Rm, is a subspace of Rn. Okay, so theorem 4.2.5. If A is an n by n matrix, then the kernel of the matrix transformation is a subspace of Rn. Okay, so every object in the kernel is something in the domain. So the kernel is made up of things in Rn, and so you can it's either a vector subspace of Rn or it's not. And to show it's a vector subspace, you can show it's closed under addition and scalar multiplication. Two vectors in the kernel are two things that T sub A maps to 0. If you add them, T sub A will map the sum to 0. So as a proof, let's x1, x2 be elements of the kernel of the matrix transformation T sub A, and let k be an arbitrary scalar. Okay, we want to show closure under addition and closure under scalar multiplication. So the question is, what would T sub A send x1 plus x2? Right? Would it send it to something in the kernel or would it not? Well, T sub A of x1 plus x2 have properties of a matrix transformation. A matrix transformation is a linear function. It's a linear transformation. And so it has what's called the additive property, that you can add it like this. You can think of this. This is one of the properties of a linear transformation. Okay. Note that a matrix something is a matrix transformation if only if it is a linear transformation. Okay, so they're one and the same. When you have a matrix transformation, it's a linear transformation. When you have a linear transformation, it's a matrix transformation. When something's not a matrix transformation, it's not a linear transformation. When something's not a linear transformation, it's not a matrix transformation. Anyway, given that it is a matrix transformation, it means it is a linear transformation, which means one of the properties of a linear transformation is that if it was t sub a of x plus y, it equals t of a of x plus t of a of y. But in this case, it's x1 plus x2. And since x1, x2 are in the kernel of t sub a, there are two things that t sub a maps to 0. So this equals 0 plus 0, which is 0. And so this shows that x1 plus x2 is in the kernel of t sub a because t sub a maps it to 0. So the kernel of that matrix transformation is closed under addition. Okay. Also, we have k as an arbitrary scalar already from our assumptions. If you take t sub a of k times x1, just choosing either of them, well, again, t sub a as a matrix transformation is also a linear transformation. There's a property called homogeneity of a linear transformation. You can move the scalar out of the function like that. And so t sub a of kx1 is equal to k times t of a of x1. And we know that t sub a of x1, since x1 is in the kernel, t sub a of x1 is 0. So it becomes 0, 0. And so that means that kx1 is also the kernel. So this shows that kx1 is also in the kernel of your this matrix transformation t sub a. And this is for any scalar, okay? Since we chose k arbitrarily, okay? We can do this argument for any arbitrary k that we choose, and so we've shown that kx1 is in the kernel of this matrix transformation for every scalar k. Okay, so the kernel is closed under scalar multiplication. Okay, and thus the kernel is a vector subspace of Rn. Okay, so that's a proof of that theorem. Okay, note, spanning sets are not unique. Okay, as an example of that, let's say, assume the space is R2. Okay, so we know that the standard matrix, the standard unit vectors span Rn. So E1, which is 1, 0, and E2, which is equal to 0, 1, span R2. But it's also true that, let's say, this vector V1, which is equal to 1, 1, and V2, which is, let's say, 1, 0, these two vectors also span R2. So they span R2 since they are non-collinear. Okay, V1 and V2 cannot be put on the same line. Okay, so since they can't be put on the same line as, and we're talking about R2, those two also span R2. So this is an example of two sets of vectors that span the same space. So spanning sets are not unique. Okay, so I gave an example where spanning sets are not unique, which means they are not unique. Okay, so theorem, if S is equal to the set V1 to VR, and S prime is equal to the set W1 to WR and to W sub K, so that's S and S prime are non-empty sets of vectors in a vector space capital V, then the span of this first set is equal to the span of the second set if only if each vector in capital S is a linear combination of the vectors in S prime, and each vector in S prime is a linear combination of the vectors in S. Okay, so the next section is 4.3 on linear independence. Okay, so in the xy plane, every vector can be expressed in exactly one way as a linear combination of the standard unit vectors. Definition: if S is equal to the set V1 to VR is a set of two or more vectors in vector space capital V, then capital S is said to be a linearly independent set if no vectors of capital S can be expressed as a linear combination of the other vectors in set capital S. A set that is not linearly independent is said to be linearly dependent. Okay, so this is the definition of a linearly independent set, and also the definition of a linearly dependent set. So we have linearly independent sets and linearly dependent sets. So every set is either one or the other, not both, and not neither. It has to be at least one of them also. Okay, so so as an example of that, for instance, if you had a set S, which is equal to the set 1, 1, 2, 2, this set S is not linearly independent, because the vector 1, 1 can be expressed as a linear combination of the other vectors in capital S. This is done by the following. So you can say that 1, 1 is equal to 1/2 times the other vector 2, 2. Okay. Note that a constant multiple of a vector is a linear combination of a single vector. Okay, we can talk about linear combinations of 10 vectors, right? Where you take each vector, you multiply it by a constant, and you add them. That's for a linear combination of 10 vectors. You can have a linear combination of one vector. It's just a constant multiple times one vector. You're not adding anything else because you only have a linear combination of one vector. So you only have one product. Okay, so 1/2 times 2, 2 is a linear combination of a single vector, namely this one. And so we've expressed 1, 1 as a linear combination of other vectors in set S. Okay, and so now this set S is not linearly independent. We can show that we found a way to find one of its vectors as a linear combination of the other vectors in the set. Okay, next is theorem 4.3.1. A non-empty set capital S, which is equal to the set v1, comma v2, comma dot dot dot, comma v sub r in a vector space capital V is linearly independent if only if the only coefficients satisfying K1 V1 plus K2 V2 plus dot 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 plus Kn Vn Kr Vr equals 0. R K1 equals K2 equals dot 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 equals K sub R equals 0. All of them equal 0. Okay. Theorem 4.3.1. A non-empty set S, capital S, of vectors in a vector space capital V is linearly independent if and only if the only coefficients satisfying this equation are when all the K's, all the coefficients are 0. Okay. So if you, this set is linearly independent if and only if the only way you can make a linear combination of those vectors equal to 0 is if all of the coefficients in that linear combination are 0. Okay. Okay. By making this statement that the only coefficients that would make this equation true are 0, that's also saying that you cannot express any of the vectors from V1 to Vr as a linear combination of the other vectors. Okay. Note, to understand this theorem and why it's true, that if there was some solution of the K's that satisfied the equation, this equation, right? If there was some solution of the K's, if there's some solution of the K's that satisfies that equation where not all of K's were 0, then you could then, well, if you think about it, if not all the K's were 0, then first notice that only one K could not be that unless the vector next to it is 0, the coefficient there cannot be only one non-zero coefficient, right? So if only one coefficient was non-zero, you'd have to multiply it by a 0 vector to get 0. So so once, right, if this was a non-zero vector and you had a non-zero coefficient, you need at least 2. And so then that means that you would have something like K1 prime, meaning the first non-zero coefficient, times, but you would have something like K sub I Vi plus dot 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 plus K sub I plus I guess I would guess to make this correct, but maybe not. You'd have a sub-index, but okay. So then you'd have this would be up to n, let's say, and so v sub I sub n. So these would be the coefficients that were non-zero, and then you'd say it equal to 0. Then you could just move things around, and so that means where the k's in the next equation are all the non-zero ones, right? And so then you could write that one of those vectors, let's say v sub I, you choose anyone you want, let's say v sub I sub 1 would then equal to the negative of the rest of it. So it'd be equal to negative k sub I, negative k sub I sub 2 minus dot 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 minus k sub I sub n times v sub I sub n, and then you would divide by the k here. So you divide this. Maybe it'll let me. No, it won't. Okay. You don't have to use parentheses. Divided by the k sub I sub 1, which is a coefficient here. And then that means that we have expressed one of the vectors in the set as a linear combination of other vectors in the set. Okay, so once we have it that there is a solution to this where not all the k's are 0, then that means that we can express one of those vectors as a linear combination of the other ones. And this is a v sub I sub 1 there, which I don't know why it wasn't there. Okay, so then but you divide each coefficient with this k, and you get a fraction times a vector minus the dot minus a fraction times a vector. So you'd have a linear combination though. Okay, and so that's why this strange condition is equivalent to having a linearly independent set, because from this equation holding for not all k 0, you could then get one of the vectors to be a linear combination of the other ones, and showing that it is not linearly independent. Okay. Example 1. The most basic linearly independent set in Rn is the set of standard unit vectors. Okay, so I already said this. Okay, and so the set of standard unit vectors is linearly independent. Wait, did I? No, anyway, okay, so you have E1, which is 1, 0, dot, 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 0. And then E2, which is the second component, is 1, and everything else is 0. Okay, they all have n components. I'm just writing more or less of those n components in each one. And then E sub n is 0, 0, 0, 0, dot, 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 0, 0, 1, where 1 is in the last one. Okay, so all the n vectors here from E1 to En is a dot, dot, dot in the middle. Those are the standard unit vectors of Rn, and it's a linearly independent set. Okay. Okay. None of those vectors can be expressed as a linear combination of the other ones. Example 2. Determine whether v1, which is equal to 1, -2, 3, v2, which is the order triple 5, 6, -1, and v3, which is equal to the order triple 3, 2, 1. Determine whether those three vectors are linearly independent or linearly dependent in R3. Okay, so to determine that, we must find whether or not there are non-trivial solutions to the equation k1 v1 plus k2 v2 plus dot 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 plus dot 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 plus kn vn equals 0. Right? A non-trivial solution is a choice of values for each k in the equation in which not all the k's are 0. Okay, so a non-trivial solution is a choice of values for each k in the equation in which not all the k's are 0. So you have to choose all the k's. You make a choice for each k where not all of them are 0, and the equation holds where both sides are equal to each other. That would be a non-trivial solution. A trivial solution would be choosing all the k's to be 0, which is definitely true because the left and right side would both be 0. Okay. Okay, so assume there is a non-trivial solution. Okay, so assume there is a non-trivial solution. K1, K2, dot, 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 Kn. Okay, so either this assumption is true and we find it, or it's false and we reach a contradiction and we show that there are no non-trivial solutions. Okay, so either we then find the solution, which is non-trivial, or we reach a contradiction that tells us that there are no non-trivial solutions. Okay, so with the assumption that there is a non-trivial solution, we have K1 times the vector B1, which is 1, -2, 3, plus K2 times the vector 5, 6, -1, plus K3 times the vector B3, which is 3, 2, 1. Okay, and it's equal to 0. And so that is a solution to that equation. And so correspondingly, we have 3 corresponding equations, one for each component. K1 plus 5K2 plus 3K3 is equal to 0. Negative 2K1 plus 6K2 plus 2K3 is equal to 0. And we have 3K1 minus K2 plus K3 is equal to 0. Okay, so we made this assumption here. Okay, so we get 3 corresponding equations from this one vector equation. Okay, and so now we want to find a solution space of that system. Okay, okay, so we want to find the solution space of that linear system, or the set of all solutions of that linear system. Well, oh, wait, so we want to find that the solution space of that linear system is non-empty, or the set of all solutions of that linear system is non-empty, or that there is at least one solution. Okay, so we want to find there's at least one solution to that system. There's at least one choice of K1, K2, and K3 that's non-trivial, in which this equation holds. We want to find that the solution space is that solution that contains a non-trivial solution, or the set of all solutions that linear system contains the non-trivial solution, contains a non-trivial solution, or that there's at least one non-trivial solution. Okay, we want to show there's at least one non-trivial solution to this linear system, at least one choice of K1, K2, and K3, which is non-trivial, meaning they're not all 0, such that this equation holds. And then that would show that the space is linearly independent. Okay, so that's what we want. What we want to do that to show. We want to do that if the space is linearly dependent. Okay, if there is a non-trivial solution, that means it's linearly dependent. If the space is linearly independent, then we will find that there is no non-trivial solutions. Okay, so 2 possibilities. Okay, if we can show that the coefficient matrix for that linear system is invertible by the equivalence theorem, that would imply that the linear system has Oh wait, okay, never mind. Let me. Okay, let's try to find the solutions. Okay. All right. So okay, so I'm going to do this on the whiteboard. Okay, so let's say you have the matrix on the left side is A, and on the right side is the zero matrix. A is the coefficient matrix. So in this problem, the coefficient matrix is 1, 5, 3, -2, 6, 2, 3, -1, 1. Right? And you have the zero, the constant 0 on the right-hand side. Okay, so we want to find solutions to this linear system. These are the coefficients of the k's. So we want to get this to reduced row echelon form using Gauss-Jordan elimination. So on the first row, I keep the same, 1, 5, 3, and then 0. For the second row, I'm going to add 2 times the first row to the second row. So 2r1 plus r2 is saying I'm taking 2 times the first row and adding it to the second one. I get a 0 here, I get a 16 here, and I get an 8 here, and this stays a 0. And then I also want to take -3 times the first row after that and add it to the third row. And what that'll do is that will get rid of the 3 there. Remember, we have so remember that we have this column here, and we have our top entry is already non-zero and a 1, and the goal is to get these other entries below it to be a 0 by Gauss-Jordan elimination. And so I got one of them to be 0, and -3 times the first row plus the third row will get rid of the other 3, and then it'll be 0, -16 here, and a -8 here, and a 0 there. And so that's the result of that. And so we have our first column looks like this. Our top entry is a 1, non-zero, and a 1. Well, everything below it is a 0. And so the next step of Gauss-Jordan elimination is, okay, stop thinking about the top row. It's still there, but move down to the next row. And then we're going to do Gauss-Jordan elimination on this. Though once you understand Gauss-Jordan elimination and getting matrices to reduce row echelon form, you can sometimes deviate from this set procedure and quickly get to the answer a little bit faster. Just a little creative thought. If you take the second row and add to the third, the third row is gone. So I'm just going to take R2 and I'm going to add it to R3. I see that the third row is just a negative of the second. And so if I add the second row to the third row is gone. So I'm going to do that. Okay, so now the third row is gone. And then now I'm going to multiply the second row by 1/16. So 1/16 times R2. And so you have 1, 5, 3, and you have this here, that's a 0. And so it's 0, 1, and then 1/2. 8 over 16 is 1/2, 0, and these are zeros, right? So we could think of the top row being covered up now, but when we look at the next row, we now have it in row echelon form. And so you would now go in backwards direction, step 6, and you would start from the bottom up, and you would want to get everything above your leading ones to be 0. So now you would look upward and you would see that this 5 above this 1 is non-zero, and you want to make it a 0. And so you need an elementary row operation that would do that. We're going from the bottom up, the bottom row is all zeros, and so we just move up to the second from the bottom row in the beginning because the bottom one's all zeros. So now we have the second row is 0, 1, 1/2, 0, and we're going to take -5 times the second row and add it to the first row, and that will get rid of the 5 above that leading 1. And so you have now 1, 0, -5/2 plus 3 is 1/2, because -5/2 plus 6/2 is 1/2, and that's a 0. So now we have our matrix here. And so this matrix is in reduced row echelon form. These are our leading ones, though I want to maybe okay, so we have that now as our matrix. And so what this says is that K1, so what this is saying that since, I guess I am going to use, I'm just going to have to use a color here. Okay, so here one is a leading one, here's a leading one there. This is saying that K1 is a leading variable and K2 is a leading variable, right? But K3 is a free variable because it does not correspond with a leading one in the matrix in reduced echelon form. So K3 is a free variable. And so you want to express K3 as a parameter. So K3 is going to equal T. And then you're going to express the other free variables in terms of that parameter. So K2 is equal to -1/2 T. And then K1 is equal to -1/2 T also. And so now we found the solutions to this linear system of the form K1 is equal to -1/2 T. K2 is equal to -1/2 T, and K3 equals T. For any real value of T you plug in, those would be the first, second, and third components of the solution. So your solutions are of the form K1, K2, K3. Where those K's are, from what I wrote up there, it's -1/2 T for K1, -1/2 T for K2, and T for K3. This is a constant multiple. T is a real value parameter. So it's T times the vector -1/2, -1/2, 1. So any T you plug in would be correspondingly giving you values of K that would be a solution. And so you see that we have non-trivial solutions. We have non-trivial solutions. We have non-trivial solutions for the case when we choose any real number for T that is not 0. So what we have to do is choose a T that's not 0, and then we get corresponding values of K, which are not all 0, which satisfy our equation. So the equation has non-trivial solutions. So thus, the equation we talked about has non-trivial solutions. Okay, and so that means that the set B1, B2, B3 is linearly independent. And our conclusion is that our set of vectors B1, B2, B3, B1, B2, B3, that set of vectors is not linearly independent. Okay, if it did not have non-trivial solutions, then it would be linearly independent. Since it does have non-trivial solutions, it is not linearly independent. Okay. Okay. So we found the solutions on the whiteboard. The existence of a non-trivial solution to the equation above, this equation, shows that the set, I'm writing the same thing again that I wrote there, the set B1, B2, B3 is not linearly independent. So it is linearly dependent by the definition of a linearly dependent set, one that is not linearly independent. Note that when you have the determinant of your coefficient matrix A is equal to 0, that implies that the matrix equation AK equals 0 has non-trivial solutions. And so this is again by the equivalence theorem, by theorem 2.3.8, or the equivalence theorem. And it's by parts B and G.
I have a quick question.
Sure.
So how would, what would tell us that it has trivial solutions? Like, what would we see that makes us know that?
You mean has non-trivial solutions?
No, so how would we know that it does have trivial solutions?
Okay, keep in mind the trivial solution is when all the k's are 0, right? So there is only one trivial solution.
Okay, so if all the k's equals 0, then it is trivial. Is that what it
Well,
means?
that's the name of that
What's that?
solution. A solution is an assignment of values to each k. If you change what your assignment of any one k, that's an entire differently solution for each. Does that make sense?
Yeah, so
So
it's non-trivial when we make it equal to 0.
yeah, and there's not only is there's and listen to how I'm saying it. I'm saying it is the only not is it is the trivial solution. It is a solution, right? When every k is 0, then you're taking a sum of zeros, and it definitely equals 0.
Okay.
So there's no information between saying that you have the trivial solution because you always have the trivial solution. So our study is whether or not there are non-trivial solutions. So you always have the trivial solution. But the question is, are there solutions where not all the k's are 0? If there is an assignment of the k's where they're not all 0 that satisfy that equation, that means I can take one of those vectors and express it as a linear combination of the other vectors. And that means that your set of vectors is linearly dependent. If there is no way to assign all the k's so that they're not all 0 that satisfy the equation, if there's no way to do that, correspondingly, there's no way to express any of those vectors as a linear combination of the other ones. And when you cannot express any of those vectors as a linear combination of the other ones, that means the set is linearly independent.
Okay, that
So
makes more sense now. I was just confused with the wording of like the trivial and non-trivial. That's why.
yeah, I kept going. So I wanted to say more because I thought maybe I could get you to know more things if I kept going around that question. So linearly independence is important because it's saying that all the vectors in your set matter. Okay, right? If you're talking about linear combinations of things, right? If you had 10 vectors and you want to talk about the set of all linear combinations of those 10 vectors, right? The best way to do it would be with the fewest possible, right? If you had 10 vectors and you had the span of them and you had a set of all their linear combinations and I added another 100 vectors, but it changed nothing to the span, right? Then you wouldn't really want them there. That would be an example of a set that's not linearly independent after you added another 100 useless vectors to that span, okay? They'd be vectors that are already in the span. And so it wouldn't make the span any bigger, these vectors, okay? But if you could add a vector in a way where it's not in the span of your original set, then the span of your new set is bigger than it was. So talking about linearly independence of a set is important. You want to know whether or not all these vectors matter in the span. If your set is linearly dependent, there'd be a way to get rid of at least one of those vectors in which the set would span the same space after you remove the vector, okay? So we want to know whether or not we're getting the span in the most efficient way possible by talking about linearly independence and linear dependence.
Thank you.
Okay, let's keep. Okay, so let's keep going. So fact, the polynomials 1x squared, comma x to the n form a linearly independent set in P sub n, which is the space of polynomials of degree at most n. This is a subspace of capital F of negative infinity, comma infinity, which is the space of all functions defined on the real line. Okay, so what am I saying here? So when we're talking about vector spaces, when we're talking about linearly independent sets, all of this stuff, we're talking about it in the context of vector spaces. Vector spaces don't just have to be vectors like physics vectors like Rn, right? Vectors are more general than that in mathematics. We can talk about polynomials being vectors. We can talk about matrices being vectors. A vector space is just a set and two operations, a team of three things that satisfy 10 axioms, right? Nowhere in our definition did we require a vector to be a physics vector, be something with a tip and a tail, and to have n components. Nowhere in the definition does it mention n tuples or vectors, physics vectors. So vectors in mathematics are more general. They're just a team of a set, an operation of addition, and an operation of scalar multiplication that satisfy 10 axioms. And so we can talk about vector spaces of polynomials. We can talk about vector spaces of functions. We can talk about vector spaces of matrices, as long as that set of things, along with whatever operation of addition you choose and whatever operation of scalar multiplication you choose, as long as those three things satisfy all 10 axioms, you have a vector space. So here, I'm introducing a vector space that is not physics vectors. It's the vector space of polynomials of degree at most n. You can show that when you have the set of all polynomials of degree at most n with standard addition of polynomials, like you add polynomials, and standard scalar multiplication polynomials, meaning you can multiply a polynomial by 3 when you multiply all the coefficients by 3, right? And you still add the terms. So you have addition and scalar multiplication of polynomials, and you have the set of polynomials. That's a vector space. And so when you have a vector space, you can talk about linearly independent sets in that vector space. Okay, so these are polynomials. When you have a polynomial, you normally think of as a sum of terms, but you can look at just one term in that sum and also call that a polynomial, right? So just like 1 plus x squared is a polynomial, x by itself is a polynomial, 1 by itself is a polynomial, x squared by itself is a polynomial, okay? Each of those things, called monomials, are polynomials of their own. And so you can make a linearly independent set of polynomials in this way. The polynomials 1, x, x squared, x cubed, dot, 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 xn. That is a linearly independent set in the space of in the vector space of polynomials with standard addition and standard scalar multiplication of polynomials. Okay, because look at it. If you have these things, there's n plus 1 of them because it's going from 1 to x to the n. You cannot express any of them as a linear combination of the others. You cannot express x to x squared as a linear combination of 1, x, x cubed, x to the fourth, up to including xn. There's no way to do it. If you multiply any of the other things by a constant, you have a constant times x to a power different than 2. And so there's no way to express any of them as a linear combination of the other things. So this is a linearly independent set in P sub n. I also mentioned that this space is a subspace of the space of functions defined on the real line. Okay, every polynomial you can think of as a function where you input a real number and the output is the value you get when you plug in the number into the unknown of the polynomial. So if you have the polynomial x cubed, you can think of the polynomial x cubed as being a function where the input is the number x and the output is the number cubed. And so you can associate every polynomial with a function defined on the real line. And so the space of polynomials can actually be a vector subspace of the space of all functions defined on the real line, because the space of polynomials is closed under addition and closed under scalar multiplication, and every polynomial can be identified as a function defined on the real line. Okay, but anyway, that's a fact. Okay, so next is a theorem. So this is theorem 4.3.2. There's 3 parts. Part A, a finite set that contains 0 is linearly dependent. So a finite set that contains 0 is linearly dependent. B, a set with exactly one vector is linearly independent. Okay, keep going. If and only if that vector is not 0. And part C, a set with exactly 2 vectors is, this I used earlier, is linearly independent if only if neither vector is a scalar multiple of the other. Okay, so a set with exactly 2 vectors is linearly independent if only if neither vector is a scalar multiple of the other. So these 3 things are very important. Okay, so when you have a finite set and one of them, and it contains 0, it is linearly dependent. When you have a set with exactly one vector, it's linearly independent if and only if that vector is not 0. And C, a set with exactly two vectors is linearly independent if and only if neither vector is a scalar multiple of the other. Keep in mind that if you have a set with exactly two vectors, if one of them is 0, then you can express 0 as equal to 0 times the other vector. And so C is kind of, you can think of A as actually, ironically, A is actually said by C. C eats up A. A is like a small part of C, even though you don't see it. Well, exactly 2. Okay, it's not. But because finite set could be more than 2, so it's not quite that. But the idea is there that if one of them is 0, you can express the other one even if it's non-zero. It's just 0 times that vector. So you would get dependence. Okay. Okay, so we have that theorem. Next is another theorem. Theorem 4.3.3. Let's S equal to V1, comma V sub R be a set of vectors in n space Rn. If R is greater than n, then S is linearly dependent. Okay, so these theorems are providing shortcuts for determining whether or not sets are linearly dependent or independent. Sometimes you have to just go by the beginning stuff. Sometimes some of these conditions happen, and you very quickly see that it's linearly independent or dependent. Anyway, this set of vectors is a set of vectors in n space. If you have, let's say you have vectors in 3 space, you had 100 of them, okay? If you had 100 vectors that had 3 components, then you would say that set is linearly dependent. You definitely have it that at least one of those 100 vectors can be expressed as a linear combination of the other 99, okay? In a sense, you could think of Rn, n space, as being of size n, of dimension n, if that makes sense. We have not talked about dimension. We will, though. But if you have a lot of vectors, if you have more vectors than the size of your space, which we call dimension, the size of the space in R3 is 3. The size of space Rn is n, is called the dimension of the space. You have more vectors than the space. You have so many vectors that you will definitely be able to find that one of them is linear combination of the others, making it linearly dependent. Okay, if you had R3 and you had 100 vectors, it is not the most efficient way to span R3 to do it with 100 vectors. You could do it with fewer. Okay, so definition. If f sub 1 is equal to f sub 1 of x, f sub 2 is equal to f sub 2 of x, comma, comma, f sub n is equal to f sub n of x, are functions that are n minus 1 times differentiable on the real line negative infinity, comma, infinity, then the determinant w of x is equal to the determinant of this matrix. Okay, so we have f sub 1 of x here. We have f sub 2 of x here. We have dot, dot, dot. Keep going with the dot, dot, dots. And then we have f sub n of x. Now, if you take this function f sub 1 of x and you do its first derivative here, that goes there. Its second derivative would go here, dot, dot, and then dot, dot, dot. And then here would be the n minus first derivative. Yes, in parentheses. Put it in parentheses. Okay, and so then you do the same thing here. You have the first derivative. You have the second derivative. Dot, dot, dot. You have the n minus first derivative. So I'm just going to change the subscript here. This is f sub 2. And so then I'm going to put dot, dot, dots everywhere else here. Speed this up. All right, so I guess I'm going to put f sub n of x prime. Good. And then we have good. So of x double prime. And then we have very good. Okay, so then this determinant is called the Wronskian of f1, f2, dot, 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 comma, f sub n. Okay, so these are functions that are n minus 1 times differentiable. So for each of these functions, f1 to fn, you can take the first derivative, second, up to including the n minus first derivative. And so you get correspondingly all the components of this matrix, and then you take the determinant, and that's equal to wx. Okay, so when you input an x value here, you put that x value into each of these functions and their derivatives, and they become entries of this matrix, and you take its determinant, and you get the Wronskian of those functions at a particular x. But the function itself is called the Wronskian of those functions, f1 to fn. So theorem 4.3.4 says if the functions f1 to fn above have n minus 1 continuous derivatives on the real line from negative infinity to infinity, and if the Wronskian of these functions, the value of that determinant, is not identically 0 on the real line, or negative infinity to infinity, as x ranges from negative infinity to infinity, not including negative infinity, then these functions form a linearly independent set of vectors in the space C n minus 1 on the real line. This is the space of all continuously differential functions of order n minus 1, meaning that they have continuous derivatives up to, they have first continuous derivative. The first derivative exists and is continuous. The second derivative exists and is continuous. Dot, dot, dot. The n minus first derivative exists and is continuous, all in the real line. Okay, so these functions are n minus c n minus 1 functions. Okay, see it says here n minus 1 continuous derivatives. That means that derivatives of order 0 to n minus 1 are continuous. Order meaning how many times you take the derivative. Okay. Second derivatives of order 2, the n minus first derivatives of order n minus 1. Okay, so you want to say that the Wronskian of these functions is not identically 0 on the real line. What that means is that there's some number value of x, real number x, you can plug in here, where the Wronskian, the value of this determinant at that x, is non-zero. That would be not identically 0. Not identically 0 just means there is at least one little x you can plug in where the value of the Wronskian is non-zero. To be identically 0, it must be 0 everywhere in the real line. To not be identically 0, there is some x in which w of x is not 0. Okay, so the conclusion is that those functions form a linearly independent set of vectors in the space that they lie in, Cn minus 1. You have a question? Okay, let's keep going. Okay, so example 8. Use the Wronskian to show that f1 is equal to 1, f2 is equal to e to the x, and f3 is equal to e to the 2x, are linearly independent vectors in the space that they lie in, which is C infinity of negative infinity, comma infinity. So what this is saying that instead of just assuming that they have n-1 continuous derivatives on the real line, instead you're saying that all orders are continuous derivatives. So if you took the millionth derivative, it exists and is continuous. If you took the 100 trillionth derivative, it exists and is continuous, yada, yada, yada. So all derivatives of any order both exist and are continuous, and they are on the entire real line. That's what C infinity of negative infinity, comma infinity means. These three functions are in that space. So I want to show that they form linearly independent vectors in that space. Okay, and so what we want to do is evaluate the Wronskian. We want to look at the Wronskian. Okay, we want to determine whether or not it's identically zero. So the question is, how do you do that? So, so here's an example. So we have the determinant of the Wronskian. Well, f1 is 1, right? So f1 is 1. If we looked at f1 of x, it's equal to 1. If we took the first derivative of f1, so we took f1 prime of x, it's equal to 0 because the derivative of a constant function is 0. And f sub 1 double prime of x is still equal to 0 because the derivative of 0 is 0. So the Wronskian here is 1, 0, 0. The first column is the first function, and then its derivatives, and you're stopping at n-1 derivative. So here it is 3. So we want the 0th derivative, the first, and then the second. And we stop at the second because we have n equals 3 because there's 3 functions, and we go from 0th derivative to n-1st derivative. For the second function is f sub 2 of x, which is equal to e to the x, which is e to the x. Well, the derivative of e to the x is itself. And so f sub 2 prime of x is still equal to e to the x. And then f sub 2 double prime of x, second derivative, is the derivative of the first derivative, which is derivative e to the x, which is also still e to the x. So this function is e to the x for all of them. So this is e to the x, this is e to the x, and this is e to the x. The 0th derivative, first and second, all three of them are e to the x. That's the second column. Each column corresponds with a function and its derivatives. So f sub 3 of x is equal to e to the 2x, and its derivative, f sub 3 prime of x, is the derivative of e to the 2x, which is 2e to the 2x. And then f sub 3 double prime of x is the derivative of the first derivative, which is derivative of 2e to the 2x, which is 4e to the 2x. Okay, so the elements here, we have e to the 2x, that's the third function. Then we have 2e to the 2x, which is the derivative of the third function. And then after that, we have 4e to the 2x, which is the second derivative of the third function. So this is the Wronskian, and it's the derivative of that matrix I found. Now, if you compute the derivative of, the determinant of this matrix, if you take it, the cofactor expansion in the first column, then there's only one non-zero entry, and it's 1. So this is equal to 1 times the determinant of the submatrix, e to the x, 2e to the 2x, e to the x, and 4e to the 2x. So when you take the determinant of that matrix, you get 4e to the 3x minus 2e to the 2x, 2e to the 3x. Okay, so e to the x times 4e to the 2x is 4e to the 3x, and then it's minus 2e to the 2x times e to the x, which is 2e to the 3x. So 4e to the 3x minus 2e to the 2x is 2e to the 3x. So that's the Wronskian. And so the exponential function e to the 3x, e to the x, and also e to the 3x is non-zero everywhere. So this function is never 0. The exponential function is always positive. It's never 0. And so the exponential function e3x is never 0. 2 times it is also never 0. So the Wronskian here is never 0. And so since the Wronskian, so we get to the extreme opposite case. We only need somewhere it's non-zero, and we get it's never 0. So since the Wronskian w of x is never 0, that means that somewhere it is non-zero. That means it is not identically 0. Don't mix up the fact that it's never 0 with that needing that much. You only need that somewhere it's not 0. And we got even more extreme case where it's never 0. And so since it's never 0, it's certainly somewhere not 0. And that's what we want to conclude, that we have a linearly independent set. So thus, by our theorem here, theorem 4.3.4, thus by theorem 4.3.4 right above, we have that the functions form a linearly independent set of vectors in Cn minus 1. Oh, yeah, C infinity there. Okay. So actually, technically, the theorem would tell you it's in C squared. So that the functions form a linearly independent set in C squared in C2 of negative infinity, comma infinity. But it's actually true that it's also C2 is a vector subspace of C infinity. And so since C2 is a vector subspace of C infinity, this also means the vectors form a linearly independent set in C infinity of negative infinity, comma infinity on the real line. Okay, so so the theorem tells us it's linearly independent in C squared, but because C squared is a vector subspace of C infinity, this being linearly independent in C squared means it's also linearly independent in C infinity. Okay, that's an important point to point out. Okay, and so another definition: a vector space, capital V, is said to be finite dimensional if there is a finite set of vectors in capital V that span capital V, and it is said to be infinite dimensional if no such set exists. Okay, definition: a vector space V is said to be finite dimensional if there is a finite set of vectors in V that span V, and it's said to be infinite dimensional if no such set exists. Okay, if you have a vector space where you can find a finite number of those vectors that span the space, it is finite dimensional. If there is no way to choose finitely many of them in the vector space to span it, then it is infinite dimensional. Okay, and so that is the end of 4.3. Okay, so next is 4.4. Okay, let me point out that that exam 2 is on December, is 2 weeks from today. It's on, I haven't announced the second exam, right? Is on December 2nd. Okay, so the second exam, exam 2 is on December 2nd in class on Zoom, when in class on Zoom, just like a normal exam would be. Okay, so exam 2 is on December 2nd in class on Zoom. Okay, so this is a major announcement. Okay, so exam 2 is on December 2nd in class on Zoom. Okay, so don't forget that. So exam 3 is going to be very soon after exam 2. So exam 3 is going to be, I'll tell you. So exam 3 is on a week after that, is on December 9th, okay, in class on Zoom. And the final is going to be during finals week. Okay, so the final is not going to be on a class day. I usually like to do that, but I need the time. So you're going to have finals during finals week. Okay, so we have the exams. So we'll have a review the class before. Okay, I'm going to need to extend class to make sure we have time for the reviews. Okay, so I will give you a review for each of these exams, the class before. Okay, so the class before each exam, I will give you a review. We will need to extend class time to fit that in. Okay. As long as you remind me to record the sessions, so I sometimes remember myself. If you remind me to record the lessons, I'll record them and I'll post it. So if you have to go, if you can't stay, it should still be recorded as long as you make sure I remember, and it'll be on YouTube. So if you have to go, or maybe you're tired, you can watch it later. But if you have questions, you're going to need to stay to ask them. Okay, so I also have office hours every week, so I can help you with anything you need, including review for exams every Friday. There's also office hour tomorrow. There's no class on Thursday of next week because of Thanksgiving, right? We have class on Tuesday, on the 23rd. Okay, so there's office hour tomorrow, and I think I may have rescheduled the office hour for next week because of Thanksgiving. So let me quickly check. Don't go anywhere. I'm going to quickly. I'm signing in, so I need to get rid of the screen share. I'm still saying some things. So here we are. So okay, here I am in the office hour. If you click Blackboard Collaborate Ultra, you then have the office hours, right? So the office hour for this week is tomorrow, right, from 1 to 2 p.m. Wait, sorry, no, this is 2:41. You're 2:31. Disregard that time. 2:31. Okay, so the office hour for tomorrow is from 2:15 to 3:15. Next week, because of Thanksgiving, I moved the office hour for next week to the 23rd. So on Tuesday, I also have an office hour, and it's from 5:15 to 6:15 on Tuesday. Okay, I chose that time for that day because I teach at 6:30, but it's the closest time I could do it to class. So I'm hoping people can make it. If you can't make it and you need another time, you can talk to me about it. I can work something out with you. But I have that time right now. So if you need help next week, also for the exams, I have an office hour anyway, even though it's Thanksgiving. It's just no, forget that. Okay, so then it'll just be at that time, right? So make note of that change. And then there's 2 more office hours, and it's at the normal Friday time. Okay. So and there's an office hour on. I'm going to have an office hour on 10th. Also. So I think I can have an office hour on the 10th. The last day of class, I think, is the 9th. I don't mind having another office hour on the 10th anyway, even though the semester's over. If you want it for help with the final, we'll figure that out when we get there. Okay, so you lost your what was your question? Which question? The review question? I said there's review, right? There's a review for each exam. So I'm going to need to extend class. Well, so there's a lot of material, and so I'm going to have to cover material leading up to the second exam, and then I'm just going to have to give the last exam on the last day. Okay, but so that's what's going to be. So you have 3 exams and a final, in addition to all the material we're covering. The other solution is to give only 2 exams. So I want to give 3 exams so that you have more exams. That's usually what students want. So I'm giving you 3 exams and the final. It just has to be the second, third one just has to be close together because of how this early in the semester you had a lot of days off for holidays, and so a lot of the material is just pushed to the end of the semester because the first month there just weren't that many classes. So the later material is closer together, and the earlier semester. So it's just how it works out. Online it takes longer. So with all these factors in, I just need to give the third exam a little bit after the second. But I'm giving a review for both of them, and I'm going to cover the material you need to. The exam is only going to be on the material we cover, okay? And you can study for the exam 3 if I cover material for it already before exam 2 if you want, okay? This just has to be done to get this all in, okay? So that is what it is. Okay, so I've told you now the date of the second and third exam, and the final is going to be during finals week. And so I'm going by the department for when that exam is, okay? I don't schedule the time of that exam. They'll tell me when they want me to give the exam on finals week. Okay, so we finished 4.3. Wait, don't go anywhere. So I want to, all right, we'll stop there. Okay, so next class, I'm going to have to extend class time, okay? So keep that in mind. We're stopping at 9:50 now. Next class, I'm going to make class a little longer. It's the class before vacation. So then, okay. So have a good night. See you all next week on Tuesday, okay? Or office hour tomorrow. You're welcome. Good night.